All right, so what we have is this article, just excerpts from an article, very short article. What we have here is a discussion of a research study that was done by a number of researchers at an American university. And so here's just a quick summary of the paper. So you have here a survey of men age 20 to 35. They have 2 years of professional experience. They're employed at one of 5 large companies that were within the sample that was the subject of this study. And there are a number of questions asked of the men who participated in the study. And they determined whether the men had children, and they asked them how they would describe their life. And so one of the things that the study found was those with kids were more likely to describe life as excellent. The men, another question was, do you divide caregiving responsibilities for your children equally or not equally with your spouse? And those who divided their caregiving responsibilities 50-50 reported that they were happier with their lives. And so the study concludes by saying equal division of labor leads to happiest dads. Okay, so what we have here is some claims that are correlation claims and some claims that are causal claims. All right, so what's a correlation claim? Well, the correlation claims in this paper are the following. Those with kids are more likely to describe life as excellent. And men who divide caregiving 50-50 report more satisfaction. Those are correlations. It's not saying why the men with kids are more likely to describe life as excellent. It's not saying why the men who divide caregiving 50-50 report more satisfaction. It's just a fact that within the scope of the study, if you look at the specific men who were sampled and you ask them these questions, this is the correlation you will find. It doesn't say why you find this correlation, but it says there is a correlation in this study among these men. Now, there are causal claims that are in this paper as well. So the title of the paper, right, is a causal claim. It doesn't just say that, oh, there's a correlation between people being happy and people having kids. It says, look, the path to happiness is kids. Kids cause happiness. Okay, that's a causal claim. And then equal division of labor leads to happiest dads. Dads, equal division causes happy dads. Okay, so that's the pair of causal claims that are being made. We have correlational claims and causal claims being made in this paper. Now, the question that we now face is, taking as true the results of the survey, to what extent should we draw causal inferences from the correlation? The data has given us a correlation, and the question is, do we draw a causal inference based on the correlation? So, what do we think? Any thoughts? Are there any concerns that you might have about accepting this as true? You might nonetheless be concerned that these may or may not be true. Maybe we're not so sure. Any reasons why we might be not so sure?
There's a sampling bias.
In what sense?
It's the survey includes people, men, 22 to 35, 2 years professional working experience, employed in one of the 5 largest global corporations, insurance, financial services, accounting, and consulting.
Okay.
These are highly paid jobs.
Okay.
So you have one variable right there which could explain why they were more satisfied with their life or their work.
Well, importantly, so I will say 2 things. So one is, one concern we may have about the study is it's simply not representative of other people, right? So we have a sample that is not representative of the population as a whole. So what we may want to say is, well, look, it's not that the path to happiness is kids. It's that the path to happiness for men who are 22 to 35, who are in the Boston area, who are employed in one of the 5 largest financial or insurance companies, in the Boston area, and who agree to participate in the survey, for them, the path to happiness is kids. So it could just be there's a sample that it's true for the sample, but the sample is not representative of anyone else. So that's one concern. But what about within that sample? What about the causal claim now? Just say, okay, fine, you're right. It's a very specific sample. We worry about external validity. Is there an internal validity problem, even for this sample? is it true that these things follow?
There can be n number of reasons why a person is happy. He may have kids, but still he may be happy with some other activity.
Now that's true, but why then would there be this systematic relationship, very strong, very, very strong relationship between happiness and kids in the data? It's true that lots of things cause happiness, not just kids, right? But to be clear, this claim isn't really that the only way to happiness. I mean, it kind of reads like that, but that's clearly wrong for the reason you just gave. It can't be that the only way to happiness is having kids. But let's say what this really means is one contributing factor is kids. So with that qualification in mind, your point is completely correct, of course, but with that qualification in mind, what about one path to happiness for men aged 22 to 35 employed by one of the 5 largest financial or insurance companies in the Boston area is kids?
Professor,
Yeah.
what are parameters of happiness or indicators of happiness to determine happiness?
Oh, just however they define it. They were just asked. Yeah, how happy are you? So, I mean, you might disagree. They may be deluded. They may be, confused as to what true happiness is. But we'll just accept whatever they report as happiness as the happiness.
So can you ask the question once again, because
Yeah. So, if we know this,
yes,
right? That men with kids are let's just say 40% more likely to describe life as excellent than men without kids. Does that mean that having kids causes you to be happy? That's
No,
the
sir.
question. Why not though? I mean, the data have a very strong correlation.
because maybe they are not practicing equal division of labor. Both the factors have to be seen, or only one study. I think.
Well, here it says men who divide caregiving 50-50 also report more satisfaction. So there's two ways. This picture says two ways. So one, if you have kids, you'll be happier. But if you still want to be even happier, once you have kids, you want to divide labor 50-50. And then you'll be even happier than that. That's the claim.
Happier than that.
Yeah. So both of them make you happy. You can do one, you can do the other, but for best results, do both, I think is the claim. But is that right? I mean, it might be right, but does the data tell us that? That's the question. Does the data tell us?
So the thing is that that means that causal is a subset of correlation, because we cannot just say that this is a causal claim till the time we have the data about anything.
So causation, well, it's possible to have causation without correlation, although that's pretty that's a little trickier. But in general, yes. Causation is a subset of correlation. So let's think about this. Let's think about why we shouldn't reach this conclusion. Now, to be clear, these were university professors who did this study, and university professors who reached this conclusion. I submit to you that there is no basis for reaching these conclusions based on this data. It may be true, just to be clear, these may be true, but the data don't tell us that it's true. I mean, maybe in your personal experience you've found it to be true. Maybe in your personal experience you found it to be true, but this data doesn't justify these conclusions, and I'll try to explain why. Okay. So first of all, right, we've already discussed, there's an external validity problem, right? An external validity, we've already defined that term. You might see in some papers you read it called out-of-sample validity or ecological validity. That's what you often see psychologists refer to it. And so, yeah, this is a sample of people who are very unlike other people, so it probably wouldn't apply out of sample. But what about internal validity? So this is this is another example. So a lot of experimental work that's done in economics and law is experiments done at universities on university students, and so it's not clear how much that tells us about anybody else. Okay. But what about reverse causation? Okay, what about reverse causation, also known as simultaneity or endogeneity? There's a correlation between people saying they're happy and people having kids. It could be that having kids makes you happier than you were before you had kids. Or it could be that people who are happy are more willing to have children than people who are miserable. They're like, I'm miserable. The last thing I need is some miserable person making me more miserable. And so unhappy people don't have kids, happy people have kids. I'm not saying that's true, but that could be true, and the data are equally consistent with that hypothesis, with that story as well. It could be that being happy causes you to have kids, not the other way around. That's one possibility. Okay. Another example, famous example of reverse causation. If you look at data on the size of police departments and on crime rates in cities, what you will see is there's a very, very strong positive correlation between a high crime rate and a large police department. Does that mean that a large police department causes a high crime rate? Now, I'm from Chicago, it may be true, but most of the time at least, we generally think it's reverse causation, right? Having a high crime rate causes you to have a larger police department. Okay. But what about omitted variables, right? This is just a raw correlation between two variables. But there are a lot of other things we know about the men in this study that wasn't included in this article. And shockingly, wasn't included in the underlying research paper either. So age correlates with having kids, right? By definition, as you get older, you are more likely to have kids. You don't become less like, if you have children at age 22, you don't stop being a person who has kids at a later age. So age correlates with having kids. But age also correlates with things like higher income, as we've discussed, having higher seniority at the place where you work, having more job security at the place where you work. And so what that means is it's not really an apples to apples comparison, so to speak, of two groups of people. The people without kids in the study are not the same as the people with kids. Not just that they don't have kids, but they're not the same in lots of other ways also. They tend to be younger. They tend to have lower incomes. They tend to have less seniority. So why, when you create this correlation between happiness and children, why don't you control for other factors that may also be associated with happiness? I mean, who's going to be happier? A person with more job security or a person with less job security? Who's going to be happier? A person with higher income or lower income? All else equal. If everything else is equal, who's going to be happier? But it didn't control. The study didn't control for those other factors. And given that age correlates with income, you're kind of comparing, not exactly, but you're kind of comparing young people without kids to more senior people with kids. Okay? So you're not making a comparison of two groups that are the same, and the only difference is whether or not they have kids. Okay? That's the problem of omitted variables. You've left out other variables that may be the cause, the true cause of the correlation. So here's another example. This is a more complicated example. People in the U.S., and I think this is true everywhere, by the way, but the effect in the U.S. is bigger than it is in other countries. People with advanced degrees make more money than people without advanced degrees, more money than people with college degrees. So if you have a PhD, you make more money than a person with a bachelor's degree who makes more money than a person with just a secondary education diploma. In the U.S., the ratio of income is about 3 times as much. So it's a gigantic jump in terms of earnings. Now that's a correlation. To be clear, that's a correlation. Now, is it causal? Now, there's a lot of research that economists have done, including myself, actually, on this question. And the answer seems to be some, but not all of it. So 3 times. Some of it is causal, like going to school really does make you earn higher income. But some of it isn't causal. Sometimes it's just that people who are really smart are also people who stay in school longer, right? So if you're not very bright, you drop out of school early. If you're really bright, you say, oh, why not? I like school. I'm really good at it. You stay in school longer. But what that means is it's not school that's making you earn more money. It's the fact that you're smart that makes you earn more money. If for some reason you are just banned from school and like randomly kicked out of school for no reason at all, it doesn't change the fact that you're smart. You'd still get a good job and you'd still make more money than the person who wasn't as smart as you, right? So this is a case where, yeah, this is a causal relationship, but not all of it is causal. Some of it is other factors.
Professor, did you apply that hypothesis to politicians?
To politicians?
So,
Yeah, I don't know. Yeah.
do you think omitted variables are equally as intermediate variables?
As intermediate?
Mediate variable or intermediate variable?
Or mediating variable? No, so a mediating variable, well, they can be. I should take that back. So there are different ways in which there can be relationships among things. So it could be, we're looking at X and Y, And it could be that X doesn't cause Y, but X causes Z, and Z causes Y. That's a possibility, right? It's also possible that there's no line from X to Y, but there's some Z that causes X. Z also causes Y. But if you change X, it has no effect on Y, and if you change Y, it has no effect on Z.
So is that an intervening or which variable it is?
Extraneous.
Uh,
Extraneous variable.
So an omitted variable, the omitted variables generally that I'm worried about are the latter case, not an intermediate or intervening variable, but rather it's that Z causes X and Z causes Y, but there's no relationship between X and Y. Okay? Yeah. But if what you're worried about is whether there's a direct relationship as opposed to an indirect relationship, then it becomes more important to worry about the intermediate or intervening or mediating variables. Okay. Selection. Okay, this is something I spent way too much of my time worrying about. So-called selection effects. Selection effects. It's a kind of omitted variables, and it's this idea that the way that people end up in your sample is different for the treatment group and the control group. So again, we're talking about treatment, who is treated. Here the treatment is kids, right, and the outcome is happiness. So how do people end up in the group of people that have kids in the sample, right? What's the selection of all the people in the world into this sample of people with kids at these companies? Well, there's a lot of things going on. So the people who are in their early 20s are younger, more likely to not have kids. Well, they're new to the company. Some of them will leave the company before they have kids. Right? So the people who have kids at the company are people who didn't just have kids, but they're people who stayed at the company. The people who are in their 20s and don't have kids yet are people who may stay or they may leave. Now, what does that have on the selection of people into and out of the company? If you're just starting off, you might be happy, you might be unhappy. But either way, you're in the sample. What happens to the unhappy people? They leave. Right? The happy people stay. So who's going to be 30 years old and still at the same company? The people who are happy at that company. Right? So there's a case where people are selecting out of the sample because they're moving to other jobs, and we don't see them in this sample. But that's a selection effect that affects people who have been on the job longer, not people who are just starting out. And it's the people who are just starting out that are less likely to have kids. All right? So that's the idea, this idea that selection, people are self-selecting through their behavior so that the sample of people with kids is fundamentally different than the group of people without kids. Okay. So another example, so often, and this is a more subtle example. This is a kind of obvious example, more obvious, this is less obvious. Many studies will say, look, in the United States, there are many states, just like in India, states, although the US system is less centralized than the Indian system, and so states have much more control over specific aspects of their law. And so in US states, researchers will often say, look, this state has really strict gun laws, and this state has really has less strict gun laws, so it's easier to own a gun, but it actually has less violence. There's less violence in the state. So therefore, having strict gun laws actually increases violence, but having more generous gun laws, easy to own a gun, there's less violence. Well, maybe not. Why? Because states that have really strict gun laws aren't the same as states that have really loose gun laws. Because there's a reason why they have different gun laws. Something that was different about these states caused them to behave differently. This could be like police departments and crime, right? Maybe the states have really strict gun laws because they have really bad violence and they're trying to find ways to reduce the violence. They're not the same as the states that don't start with a high baseline level of violence, for example. Okay, another example of selection, another form of selection. Look, this goes to external validity. If we're saying that having kids causes you to be happy, then presumably the advice is, hey, if you don't have kids and you want to be happier, have kids. But here's the problem. It could just be, some people, kids make them happy, and some people, kids don't make them happy, right? And maybe the kids the people who kids made happy, they already had kids. And maybe everybody else really shouldn't have kids because like there's a reason they didn't have kids, right? So on average, we might think that people self-select into which group they are. And just because in this sample people with kids are happier doesn't mean that if we went out and told everybody to have kids, that everybody would be happier, right? So that's another kind of selection effect. And here's kind of a silly example. Look, 90% of people prefer to use right-handed scissors. But does that mean the other 10% of people should start using right-handed scissors? Or does it just mean the other 10% of people are left-handed? Right, okay, so that's kind of a silly example. All right, observer effects, like we talked about this morning. This was a survey. So it wasn't like there's just data that was collected. People went out and asked them, are you happy? So you might imagine you just told a researcher that you're 35 years old, you're a vice president of a company, you're making $1 zillion, and you have a bunch of kids. And then they ask, so are you happy with your life? And you might think to yourself, if I say no, I'm going to sound like the biggest jerk in the world. So there might be sort of an observer effect, which is, men who are married with kids, who have high incomes, might feel obligated to say, yes, this is great. Well, maybe, you're 22 years old, and it's not cool to say you're happy, I don't know about 22-year-olds anymore. That was a long time ago for me. So anyway, so it depends on how the study was done. I actually don't know how anonymous the study was done, so I don't know if this is a big effect or not, but it's a possibility. So observer effects is what they're called. So here's the most famous example of observer effects. It's actually, observer effects are sometimes called Hawthorne effects. I don't know if you've heard that term, Hawthorne effect. I'm sorry? Yeah. So the Hawthorne Works factory, it's actually in Chicago, so it has a Chicago connection. So there was this factory like 100 years ago, almost 100 years ago, and they wanted to experiment. They wanted to see ways to improve worker productivity. So what they would do is they would go in at night and they would change like how bright the lighting was, or like how close the tables were to the chairs, and then they would see if productivity went up the next day. And the funny thing was, every time they made a change, productivity went up. And so they started to suspect that it's not that the changes had an effect, it's that the workers knew they were being watched. They were working harder because, like, oh my gosh, somebody's watching me. I can't just pick my nose all day, right? So, so that maybe it's observer effects. And then misspecification. This is really just another version of omitted variables, but again, it's a term that you'll come across, so it's worth talking about. Notice, what's another really important variable that wasn't included in their correlation between having kids and being happy? What about being married? Maybe being married makes you happy. And being married is correlated with having kids, right? Men who are married are much more likely to have kids than men who are unmarried. It's not a perfect correlation, but it is a strong correlation. And if marriage is highly correlated with having kids, and you're comparing men with kids and men without kids, that means you're also comparing married men to unmarried men. And so they could have just as easily titled the survey, right, the path to happiness for millennial men is marriage. Right? It's an equally strong correlation. And yet by not including marriage as a control, we don't know whether it's marriage that's the effect, the cause, whether it's kids that's the cause, or something else entirely. So in other words, the key here is that treatment and control groups, the group with the treatment and without the treatment. So if you want to know the effect of kids is the treatment, no kids is not treatment. You have to find a way to make those two groups comparable, right? Equivalent in every other way, but the one way that you want to affect them. Now, the gold standard is going to be, we're going to talk about this a lot over the course of the week, it's going to be an experiment, a randomized controlled trial, where you randomly assign treatment to people. You can't do that with kids, right? You can't take a group of people and say, okay, we're going to flip a coin, and if it's heads, you can't have a kid. And if it's tails, we're going to force you to have a kid. Like, you can't do that, right? And that's why we have to use observational methods, right? But that's the goal of the observational method, is to make the treatment and control groups as similar as possible. And clearly, if you're not even controlling for whether or not you're married, they're not that similar. And here's another example. It's actually from the Hawthorne study itself. It turns out they made their lighting changes once a week, and they always did it on Sunday night. And Sunday was the one day the workers had off in the factory. And so they would always check to see if the intervention, the changes they made on Sunday night, had an effect on Monday. And they always found that productivity was higher on Mondays than on Fridays. But is that the effect of changing the lighting, or is that the effect of you've had a day off, you come back and you're refreshed and you're more productive, right? So it's another example of omitted variables or misspecification. Okay. And here's maybe my favorite comic strip. There's this online comic strip called XKCD. And this is the lesson here. Get it, right? Okay. I used to do correlation applied causation, then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Maybe it helped. Like, do we know that it has a causal effect, or is that just a correlation? Right? Okay, so that's the idea. That's the basic idea, right? So correlation does not imply causation, right? That's, you've heard this before probably, but you can't say it enough. It bears repeating. But of course, it's not useless. Right? It's still evidence of something. The question is it evidence of causation or not? It could be. It's at least indicative that there may be some important causal relationship. We just might not be sure what it is yet until we examine more closely. Okay? And of course, it could just be random chance, as we talked about. And we'll spend a lot of time tomorrow talking about how to tell whether it's random chance or not. That's a big part of what statistical statistical significance testing deals with. Is this random chance, or is this, in fact, due to some kind of statistical relationship? Okay. So in other words, what we need to do is we can't just rely on correlation. We have to look for some reason to think. We have to have good reasons based on looking at the way the study was designed for concluding that that correlation is in fact evidence of causation and not just due to omitted variables or reverse causation. All right, and that's basically the goal of the economic approach to empirical legal studies, is to design the study so that you don't have the problems this study had. You design the study so that when people read it and they see all the things you accounted for and you thought about and you incorporated into your analysis, that in the end they say, yes, I really do believe that this is a causal effect. That's the goal. And we're going to talk about how to do that. I'm going to read papers that do that. Some of the papers do it better than others, but all of them make a contribution in that respect. Okay. Now, before I go on, actually, before I go on, saying before I go on, any quick questions or anything along the line? So then, but although we will spend a lot of time talking about causation, I do want to emphasize that not all empirical questions are about cause and effect. And so, and there's two kinds of empirical questions not about cause and effect that are still very, very important empirical questions. And so I just want to make sure that we take a moment to make note of them. So one is what you might call a purely descriptive. It's just about measuring. So if the question isn't, do men aged 22 to 35 at large insurance and financial firms, do kids cause happiness for them? But instead of the question simply is, what percentage of men at those firms have kids? Right? There's no causal claim there. You just want to know, like, how many kids? And so sometimes all you want to know is just how much. You just want to know the amount or something. So an important question, we'll read a paper tonight. You will read a paper, or tomorrow morning, whatever. You will read a paper about, like, look, how long do cases spend in the Supreme Court before the Supreme Court decides them? Right? We're not asking what causes delay in the Supreme Court. We're not asking how to fix it. We just want to know, does it take a year? Does it take 5 years? Right? We don't need causation. We just need the number, right? So it's a pure measurement exercise. So that's one kind of question. Sometimes we don't even know just how much of something there is, and we just want to measure it. So that's a very important category of empirical legal studies. And I just want to emphasize that we're not going to talk about that kind of study that much. We'll talk about it a little bit tomorrow, and we're reading the paper and we'll talk about it. Professor Bajpai, who we're also going to read a paper by him. It's another important measurement exercise. We're just trying to understand like what's actually happening, right? In these cases, it's a case about witnesses and how witnesses are treated in the court process. Like, do we even know how witnesses are treated in the court process? Before we can even make any claims about whether the legal system is causing witnesses to have a certain experience, we need to know whether or not they're having that experience, right? And so there's a tremendously important question there. Just, let's go out and find out what's happening to witnesses, right? And so we're not going to spend a lot of time talking about these kinds of papers because the problem of correlation versus causation is going to soak up a lot of our attention. But I don't want to skip over the fact that really the first step in any major empirical project is just getting the basic facts on the table, right? And so that's why we're going to read some papers for tomorrow that are really fundamentally about just getting the facts right, So that's tremendously important. And then the second kind of study, and this is something we won't spend as much time on, but it's an interesting type of study, and it has some important applications in modern practice. Is a study where, we are looking for correlations. It's not just getting facts. We're looking for correlations. We're going to do statistical analysis, and we're going to generate a correlation. But we don't care about causation. We really are just looking for the correlation. Okay, so what do I mean? When does that happen? Okay, so this is the sort of the prediction versus causation question. Now we still care whether it's random chance or not. So we talked about that. We still care whether or not it's random chance, but we don't care whether it's a causal relationship. Now, how can that be? Why do we care about a correlation just for its sake? Well, it's when what we care about is predicting something rather than causing a change. Okay, so I'll be a little more clear about this. So there's this great paper, for those of you who want the slides, you can look up this paper at some point. It makes a very simple point. I'll summarize the paper for you in one slide. It's not that complex a paper. But amazingly, this is the AER, the American Economic Review. This is the #1 economics journal in the world. Amazingly, it apparently took economists until 2015 to realize, like, oh, we don't always need to know causation. Sometimes we just care about correlation. And here's how they explain it. Sometimes correlation is all we care about. So, for example, if the question is, there's a drought, and we're trying to end the drought. We need to cause it to rain. So the question is, should we do a rain dance? Should we do an elaborate dance, to appeal to the gods of the rains or whatever it is, in order to cause it to rain? So the question, should we do a rain dance, is a question of causation, right? Not are rain dances correlated with it raining, but do rain dances actually cause it to rain? On the other hand, let's say it's kind of cloudy. And you're care about, these are not questions that law professors or lawyers or judges care about, but there are questions like this in the law. So for example, setting bail. I don't know as a matter of so what's the doctrine on setting bail in India? What factors can be taken into account when you're setting bail? Anyone a criminal law? So yeah.
As Justice Krishnaiyer said, bail is the rule, jail is an exception. So in most of the cases, if an accused does not have a criminal background or is not likely to tamper evidence or victimize any witness, he is likely to get bail.
Okay, so the question is, we're concerned about whether there's going to be witness tampering or witness intimidation or something.
Degree of punishment is also taken into consideration.
Sorry?
Suppose that if the punishment is higher, then there is less possibility of reveal of it. If there is
The nature of the offense.
punishment.
Okay. Yeah, so it's very similar in the United States. So the factors in the United States are primarily, is this person a flight risk? So in other words, are they going to just skip bail and try to flee the country? And are they likely to somehow interfere with and so here's the key. If you're a judge, a magistrate or a judge who's asked to set bail, you don't need to know what causes a person to commit a crime. You don't need to know what causes a person to tamper with witnesses. You don't need to know what causes a person to flee justice. You do need to know what predicts whether a person will flee justice, what predicts whether a person will intimidate witnesses or will commit crimes. And so you look at things, right, like prior convictions, age, marital status. And importantly, you're not asking whether this causes future dangerousness, you're asking whether it predicts future dangerousness. So it may be, so for example, take marital status, right? It may be that people who are married, being married causes them to commit less crime or not to flee. So let's think about flight risk. Okay? Being married, you know, the old joke about, oh, I'm tied down, right? I'm tied down, I'm married, old ball and chain. But you know, maybe that's true in the sense that you're less likely to actually flee because you know your wife or your husband and your family members they put pressure on you, right? Not to flee. Okay, so that's a causal effect. Maybe there is no causal effect. Maybe it's just the kind of people who get married are the kind of people who don't mind, sticking around, right? People who are always like running away to the next thing aren't the kind of people who get married. So maybe there's no causal effect at all of marriage, right? Marriage is caused by a person's personality, and flight risk is caused by a person's personality, but there might be no causal relationship between the two. But if you're the judge setting bail, you don't care. All you need to know is this person married or not? Because that's a good predictor of flight risk. That's the idea. Okay. So the point here simply is it depends on the question you're asking. Right? It just depends on the question you're asking. Obviously, in a lot of criminal justice questions, we really do care about causation, right? We really do care about causation. If we want to, create a new crime, define a new crime or a new punishment, we want to know what effects that crime causes, right? Okay. Any questions about this sort of description versus causation? Prediction versus causation question. Okay, and then this description versus. Oh yeah.
Clearly, it requires something more than mere correlation to make a prediction.
Yes, right. So presumably, the reason something is a good predictor is because there really is, and this goes back to the earlier question, there's got to be something to the correlation, right? So if the correlation is the product of mere chance, then that means, by definition, if it's just luck that a correlation exists in the data, that means it's not going to happen again in the future. Right? So in order to be a good predictor, it can't be a correlation that's due merely to chance. There has to be some causal connection or some omitted variable or something that means these two things will consistently be correlated in the future, not just in the past. Right? But what we don't care about is whether there's a true causal relationship or if there's just omitted variables that are causing the relationship to occur. Because either way, as long as it's a strong relationship, we can rely on it in the future. But it's true that if a correlation arises merely by chance, so to go back to the example from earlier, the Super Bowl, the American football example, the Super Bowl for 25 years almost perfectly predicted the stock market. So that was observed in like 1997. How good a predictor do you think it was after 1997? It turns out it predicted the stock market exactly 50% of the time, which is of course how good any predictor is when you're predicting whether something goes up or down. Right, so it's always going to be 50% accurate because it's predicting one of two things. It's no better than throwing darts at a dartboard. Right? So even though there was a strong correlation, because it was due to random chance, it was a terrible predictor. It wasn't just a lack of causation; it was also a lack of prediction. Right? It's a completely what you call spurious correlation, completely due to chance.
Professor, do you find any connection between prediction and null hypothesis?
Yes, we will talk about null hypotheses. I might get to it. No, we're not going to get to it today. Yeah, tomorrow. We'll talk about null hypotheses tomorrow. So the idea is when we talk about hypothesis formation, what we talk about there is saying we're going to make a prediction, right? It's not that the data is generating, allowing us to make predictions. We're going to make a prediction and we're going to test that prediction against the data. So we'll definitely talk about prediction, a different a different sense of the word prediction in exactly the context you described. Okay, so description versus prescription. This, I think you'll find quite intuitive, but it's important, so I want to mention it anyway. So as I said before, facts are important. Facts are very important to making questions about what the law should be, to normative questions, to policy questions. I want to be clear when I say this what I mean. What do I mean? I mean empirical work is descriptive and it's positive. What do I mean by that? So descriptive is just, it's saying, look, these are the facts. We're measuring quantities. Okay, fine. It's positive. What I mean by positive science, I mean positive as opposed to normative. I mean positive in the sense of, I'm not judging whether something's good or bad. I'm simply saying this is how the world works. I'm simply saying X causes Y. I might be happy about it, I might be sad about it, but X causes Y. That's a positive claim. Empirical work is not, in itself, normative or prescriptive. Right? In other words, empirical work cannot tell you whether something is good or bad. Okay? That is the job of ethics and moral philosophy and religion and other things. But empirical data cannot tell you whether something is good or bad. Now you can look at the data and you can conclude that, oh my gosh, this is bad, but the data itself can't tell you that. And empirical work is not itself prescriptive, right? It can't tell you which policies to pursue and which policies to reject. That depends on normative values. Like, what are our values? Like, so the idea here is simply that empirical work can get you part of the way, but it can't get you the whole way, right? What our normative commitments and our values are will affect what we prescribe. But empirical work will get us part of the way there. It's a crucial component to any policy question. So that's the basic idea. Description does not imply prescription. So here's an example. I'm probably getting this number wrong. I need to check. I have this data, so but I'm not sure I've updated this number. So if you look at cases decided by the Supreme Court of India on the merits, SLPs that are admitted for merits hearings and appeals, that sort of thing, you see that, I think it's a little bit lower than this, but let's just say for the sake of argument, the government wins 70% of the time. Okay? So the government wins 70% of the time. It might be slightly lower than this. Okay, well that's a fact. I mean, it's just, we look at the data, in the years we looked at, it's 70%. Okay, that is description. We have described what happens. But that's all we've done, okay? We have not explained why the government wins 70% as opposed to 50% or as opposed to 20% of the time. That's a positive question. Maybe empirical data could help us answer that. If we had data about, if we had a theory and data that helped explain what causes different parties to win and lose in the Supreme Court, that's a question that I'm actually working on with my co-authors, but we haven't answered it quite yet. And it certainly doesn't tell us whether this is a good thing or a bad thing. Maybe it's great that the government wins 70% of the time. Maybe it's terrible that the government wins 70% of the time. Maybe it's completely neutral, but the data can't tell us that, right? And of course, it doesn't tell us what to do about it, right? That's the prescriptive part. So I just, kind of like this path to happiness for millennial men as kids thing, like, sure, that's a fact. In this sample of people working at these companies, this age, this correlation exists. Fine. But that doesn't tell us that we should tell people to have kids or not, right? That's not what the data justifies. The data can just tell us, maybe, ideally, at least descriptive facts, and ideally also maybe helping answer positive questions. But sometimes, we can't even get that far. Okay. But it's important to keep all of these concepts separate. Okay. Any questions? Okay, so how are we doing for time? We've got a little bit of time left. Okay, so what I'm going to do is I'm just going to begin basically the materials for tomorrow. Tomorrow is probably going to be, it's going to feel like the longest day because it's going to be statistics, and we're just going to be talking about statistics for the day. I'm minimizing the amount of mathematics in this course. It's going to be extremely, very, very small amount of math. I'm going to really just talk about conceptually, like the concepts involved in statistical analysis. I'm not if you came here hoping for me to like teach you how to write program in Stata or SPSS, I'm not going to do that. More important than the technical stuff is understanding conceptually when somebody does, or when you do it yourself, when you run a regression, like what does it really mean to say the p-value is 0.05? What does that even mean? Okay, that's what we're going to talk about. Okay, but in order to talk about that, we do have to introduce some of the basic concepts. Not very much math, but some statistical concepts. So let me get started with that. Again, we're going to start with really basic stuff and work our way up, just like we're doing with everything else. But we'll spend just the next 10 minutes today, and then we'll spend all day tomorrow talking about different sort of interesting aspects of statistics and regression. Okay. So let's just get going. Okay, so summary statistics. In other words, this is the kind of stuff that's like, what are just the basic facts? We're not no regressions, no correlations, no causation, just getting the numbers out there. That's summary statistics. Okay, so what should we do? Well, I'll say this, even if what you're trying to do is answer a prediction question or a causal question, you always want to start with description. Before you get to causation, you want to start with description. Just get the summary information. Summarize the data. Okay, that's what summary statistics is, summarizing the data. And so the best and first place just to go to start with in a paper, whether you're writing it or reading it, is summary statistics. Okay, so what are summary statistics? Well, they're measures of central tendency. Average, right? That's what people mean when they say something's average. It's the central tendency, what's kind of in the middle of the data. Measure of dispersion, right? How spread out is the data? Is it really variable, or is it all kind of the same? Okay. And then distributions of variables. Are there just kind of one big hump in the middle, or is it kind of two humps and kind of nobody's in the middle, or that's the idea. Okay, so that's what we're going to talk about. All right, so let's just define some basic terms. So imagine you've got a sample. It's a very small sample. You've only got 7 observations, 7 data points. So you want to measure how many plaintiffs in an average case, and you're really short on time. You've only got 7 cases in your data set, but hey, 7 is better than none. So you pull 7 cases and you count the number of plaintiffs in each case, and this is what you count. This case had 1 plaintiff, 1 plaintiff, 1 plaintiff. This case had 2 plaintiffs. This case had 3 plaintiffs, 6. I don't know what somebody did, but they made a lot of people mad. 21 plaintiffs. Okay. So that's your data set. Okay, what's the mean? The mean is the average, right? So you just add up the number, divide by the number, right? So add it up, divide by n, so it's 7. So it's 35 divided by 7 is 5. Okay? Now notice, when you say something's average, the average value might not even be in your data. Right? So we say, oh, the average case has 5 plaintiffs, even though no cases have 5 plaintiffs. Okay? So that's an important quality of the average. It may be in your data, it may not be in your data, but it nonetheless, even though there's no 5 in the data, the number 5 kind of summarizes this data in one way that's useful. Now the median, most of the times when people say average, what they think they're saying is mean, but what they really mean is median. What does median mean? It means the middle of the list. It means if you go from biggest to smallest, who's in the middle? Who's has 50% of people above them and 50% of people below them? That's the median. So the median on this list is 2. And by definition, the median on any list actually is in the list, right? Okay, that's the idea. With one technical exception, which we'll ignore for now. And the mode is the most common value. So oftentimes we'll hear economists say, well, what's the modal outcome? All they mean is what's the most common outcome. They're just trying to sound smart. So what's the modal value in this data? Well, the modal value is 1 because it shows up more than any other value. So just making sure we got the terms in our minds. What's the range in the data? Well, the range is just 1 to 21. Okay. What's the variance? It's a little bit harder to describe, but the variance is a way of measuring whether the data are tightly bunched together or widely spread out. And the way that you calculate the variance, for those of you who are getting lost at this point, don't even worry about it. For those of you who care, the way the variance works is you calculate the mean first, then you take the difference between each of these numbers and the mean, you square each of those differences, add up the differences, and divide by n. So if the mean is 5, the difference between 1 and 5 is 4, and the square of 4 is 16. Okay, and you do that for all of them. You add them all up and divide by 5, and you get the variance, 45 plus 4. The standard deviation is just the square root of the variance. So there are just two ways of measuring variance. And then the standard error is yet another way of measuring variance. It's the standard deviation divided by the square root of n. Now, again, for those of you who don't care about the math, none of these details on how to calculate them is important. What is important is to understand that these are all measures of how spread out the data is. And if the number is bigger, that means more spread out. And if the number is smaller, that means less spread out. Okay, that's basically the idea. Okay. All right. Any questions so far? Okay. A histogram. You may be familiar with this term, but if you're not, it's a really neat thing. A histogram is just a graph showing the distribution of something. So how many is this axis? How many? And this is what value, right? So you've got 3 cases with 1, and you've got 1 case with 2, and you've got 0 cases with 5, right? So that's how you count. You just draw a histogram that way. Of course, it's much easier to get the computer to draw the histogram, but that's how you do it. And you'll hear about skewed. The distribution is skewed as opposed to symmetrical, right? So a distribution is symmetrical, right? The distribution that's skewed is kind of like this, right? And so this distribution is skewed one way. It's skewed to the right because it points to the right, right? The fat end is here, the thin end is here, so it points to the right. So it's skewed to the right. Now here's another distribution, right? Not a randomly chosen distribution, right? Very deliberately chosen distribution. Many of you may have seen distributions that look like this before. This is called a normal distribution, or a bell curve, right? Or for those of you who are into statistics, a Gaussian distribution. I'll call it a normal distribution. So what do we know about the normal distribution? Well, it's unimodal. What does unimodal mean? Well, it has one mode, right? It has one most common value. This is the common value, right? The one that shows up a lot. And it's symmetric, right? It's not skewed right or left, it's balanced. Okay. You'll notice that the mean equals the median. That's true for any symmetric distribution, if you're keeping track. But in any event, it also has these qualities, which may seem not particularly interesting or important to you at the moment. I promise I will explain very soon why we care about these numbers like 68, 95, and 99.7. So this is just saying standard deviations of the mean. So again, the standard deviation of a normal distribution is how spread out it is. So a normal distribution with a really big standard deviation is going to look like this. A normal distribution with a really small standard deviation is going to look like really pointy and tall. Because if it's pointy and tall, that means all of the numbers are really in this middle, and there's not very many numbers at the edges. If it's spread out, that means there's still a lot of values that are way out on the edges, right? Okay. In any event, but all normal distributions, no matter how spread out or how thin they are, have the following property, which is within one standard deviation of the mean, 68% of all of the values are in that range. So 68% of, so remember, if we just count up, we have a sample that looks like this. When we count up all the values, look, there's 2 that have this value and there's 8 that have this value. 68% of all of them are going to be in this range. And that's what it means to say 68% fall within one standard deviation. 95% fall within 2 standard deviations, and 99.7% of values fall within 3 standard deviations. The mean. So here's an illustration color-coded for our convenience. So here's a normal distribution. This blue area is the area that is close enough to the mean that it is within 2 standard deviations of the mean. 95% of the area under this curve is blue. Okay, that's what it means. So 95% of the area under this curve is blue. That means 95% of the observations or data points that are represented by this histogram are this close to the mean, and the rest are really, really far away. They're more than 2 standard deviations away from the mean. Okay. Now, what does it mean when I say 5%? So this is 95%. That means this is 2.5%, and this is 2.5%. So this is the tails, as it's often called. These are the tails of the distribution. This will become very important when we start talking about null hypotheses and hypothesis testing. So 5% in the tails. Okay. All right, so I will end on this final note, which will may make very little sense to you, but I promise will be useful for tomorrow. So here's an important property of the normal distribution. And again, you don't actually have to understand this. This isn't a course in math or statistics. This is just a stepping stone to get to something that is important to understand, but we're just not there yet. So imagine you want to measure the mean of a variable. There's something you want to measure that's important, and you want to estimate it because you don't know its value. All right. You're going to take samples from the population, and you're going to statistically study those samples by calculating the average value that you find in the population. And if you imagine now in real life you only get to take a sample once sometimes, but imagine in principle you could take many, many samples. Many, many samples. And each sample is going to be a little bit different. The estimate you calculate based on each sample will be different just by random chance, because you sample different people in the population, different cases in the population. But you calculate the average value, the estimated average value from each sample, and then you draw a histogram of all of the average values in the population. Here's the amazing thing, is if you do this enough, if you draw a large enough sample of samples, then the distribution of the means, the estimates that you calculate based on those samples, will have a normal distribution, period. No matter what you're studying. You could be studying people, animals, you could be studying cases, you could be studying clouds and rain, it doesn't matter. If you take a large enough sample and you calculate the mean values, the average values, estimated values from every sample, and look at the distribution of those estimates, it's going to be a normal distribution. Now, why is this important? And I'll end here. Why is it important that it's going to end up being a normal distribution? Because that means that when we just take one sample, because we can't infinitely sample from a population to determine what the characteristics of the population are. We have to just take one sample. We can use the properties of the normal distribution to extrapolate from our one sample to what an infinite number of samples might look like, and thereby help us to determine whether the sample we've drawn tells us something very compelling or very weak about a correlation in the data. Okay? So the idea here is we're going to use the normal distribution to help us judge how strongly our sample from the data helps us either accept or reject the hypothesis that we're trying to test using the data. And the normal distribution is what allows us to do that statistically. Okay, so I will review this very quickly at the beginning of the day. Tomorrow we'll talk about what it means to do hypothesis testing using statistics, using the central limit theorem. Again, you don't have to know the central limit theorem. I'll talk about it for 10 minutes at the beginning of class tomorrow, and then I'll never mention it again. But the idea is that the fact that once you get beyond 2 standard deviations, it's 5% of all data points in the distribution are in those 2 tails. That 5% number is going to keep coming up again and again, and that's why I wanted to show you that picture. That's where the 5% number is coming from. When people talk about statistically significant at the 5% level, okay, that's where we're going with this. Okay, but that's for tomorrow. And again, you don't need to actually understand any of the statistics. All of this is just to get us to talking about statistical significance of the 5%. Okay, so let's take a break. There'll be a discussion session at 4:45, I think. So if you have questions about this, we can talk about them. I also have a neat handout on senior advocates in the Supreme Court. So we'll talk about causation versus correlation using that example as well. Okay, so I'll see you in 10 minutes.